Life on Earth has shown remarkable resilience, adapting and thriving through billions of years of catastrophic changes and environmental upheavals. Despite this tenacity, the planet's biosphere remains vulnerable to a range of existential threats. From asteroid impacts and gamma-ray bursts to deoxygenation and the eventual aging of the sun, these potential doomsday scenarios reveal the fragility of life and underscore the need for humanity to understand and prepare for such catastrophic events. This essay explores these scenarios in depth, examining their mechanisms, historical contexts, potential impacts, and the lessons they impart for the future of humanity. Life's journey began approximately 4 billion years ago, under a barrage of harsh conditions. During this period, often referred to as the Hadean Eon, Earth was a tumultuous environment characterized by intense volcanic activity and frequent asteroid impacts. Despite these hostile conditions, simple microorganisms emerged, marking the dawn of life on our planet. These early life forms laid the foundation for the rich tapestry of biodiversity we see today, demonstrating life's extraordinary ability to adapt and persist even in the face of extreme adversity. Throughout Earth's history, life has faced numerous mass extinction events, driven by dramatic shifts in the environment. These events, ranging from asteroid impacts and supernovae blasts to massive volcanic eruptions and abrupt climate changes, have eradicated a significant proportion of existing species, only for life to rebound and new species to emerge. This cyclical pattern of destruction and renewal highlights the resilience of life, yet also underscores the potential for future catastrophic events to threaten its existence. Asteroid impacts represent one of the most dramatic and well-documented threats to life on Earth. The most infamous example is the Chicxulub impactor, a city-sized asteroid that struck the Gulf of Mexico approximately 66 million years ago. This cataclysmic event is widely believed to have caused the extinction of the dinosaurs and many other species, reshaping the course of life on Earth. The mechanism of destruction in such an event is multifaceted. When a large asteroid impacts Earth, it releases an enormous amount of energy, comparable to millions of nuclear bombs detonating simultaneously. The immediate effects include intense heat, shock waves, and the ejection of massive amounts of debris into the atmosphere. This debris can block sunlight, leading to a nuclear winter scenario in which global temperatures plummet and photosynthesis is disrupted. The resulting collapse of food chains can trigger widespread extinction. The Chicxulub impact serves as a stark reminder of the potential for asteroid impacts to cause rapid and extensive biological upheaval. Despite the dramatic impact of the Chicxulub event, the probability of a similarly large asteroid striking Earth in the near future is relatively low. Based on the geological record of cosmic impacts, NASA estimates that Earth is struck by a large asteroid capable of causing global devastation roughly every 100 million years. However, smaller asteroid impacts occur more frequently, with evidence suggesting that some people may have been killed by small meteorite impacts within the past few thousand years. Nonetheless, simulations published in Nature suggest that an asteroid large enough to wipe out all life on Earth would need to be truly gigantic, capable of literally boiling away the oceans. Asteroids of such size, like Pallas and Vesta, are extremely rare and are not currently on a collision course with Earth. Modern technology offers some hope for mitigating the threat of asteroid impacts. Space agencies, including NASA and ESA, have developed programs such as the Double Asteroid Redirection Test, DART, to test methods for deflecting potentially hazardous asteroids. While these efforts represent a significant step forward in planetary defense, they are still in their early stages and may not be sufficient to prevent all impact scenarios. In addition to asteroid impacts, Earth faces the potential threat of deoxygenation events. Oxygen is essential for most complex life forms, and fluctuations in atmospheric and oceanic oxygen levels have historically had profound impacts on biodiversity. The Great Oxidation Event, GOE, which occurred approximately 2.5 billion years ago, was a pivotal moment in Earth's history. Driven by the activity of cyanobacteria, this event marked the first significant increase in atmospheric oxygen, enabling the evolution of aerobic organisms and paving the way for complex life forms. Conversely, a significant decrease in oxygen levels can lead to widespread extinction, particularly in marine environments that are highly sensitive to oxygen availability. The late Ordovician mass extinction, which took place around 450 million years ago, is a prime example of the devastating impact of deoxygenation. During this period, Earth experienced a dramatic drop in oxygen levels, resulting in the extinction of over 80% of marine species. The exact cause of this oxygen decline remains debated, but it likely involved a combination of climate cooling and changes in ocean chemistry. Modern concerns about deoxygenation are closely linked to climate change. Rising global temperatures are reducing oxygen levels in the oceans, a phenomenon known as ocean deoxygenation. Warmer water holds less oxygen, and changes in ocean circulation patterns can disrupt the transport of oxygen to deeper waters. This trend poses a significant threat to marine life and could potentially trigger a new mass extinction event if left unchecked. Addressing climate change through the reduction of greenhouse gas emissions and the implementation of sustainable practices is crucial for mitigating ocean deoxygenation. Protecting and restoring marine ecosystems, such as coral reefs and mangroves, can also help maintain oxygen levels and support biodiversity. Gamma-ray bursts, GRBs, represent another potential threat to life on Earth. These mysterious events are among the most energetic and violent explosions in the universe, capable of releasing more energy in a few seconds than the Sun will emit in its entire lifetime. A GRB directed at Earth could have catastrophic consequences. The intense burst of gamma radiation could deplete the ozone layer, exposing the planet to harmful ultraviolet UV radiation. This increased UV exposure could devastate the biosphere, particularly affecting organisms that live near the surface of the oceans and on land. Additionally, the gamma radiation could disrupt atmospheric chemistry, leading to the production of nitrogen dioxide, a pollutant that blocks sunlight and could trigger a global cooling event. While GRBs are typically observed in distant galaxies, and the probability of a nearby GRB affecting Earth is low, the potential impact of such an event is severe. The lack of direct observations of nearby GRBs makes it difficult to predict their potential effects on Earth with certainty. There are currently no known methods to prevent or mitigate the effects of a GRB, making it a largely uncontrollable threat. Understanding GRBs and developing early warning systems to monitor cosmic events that could pose a threat to Earth is crucial for preparing for such scenarios. Even if humanity were to survive asteroid impacts, deoxygenation, and gamma-ray bursts, the eventual fate of Earth is tied to the life cycle of the Sun. The Sun, which has provided stable energy for billions of years, will eventually evolve and become hostile to life on Earth. As the Sun ages, it will exhaust the hydrogen fuel in its core and expand into a red giant. During this phase, expected to occur in about 5 billion years, the Sun's outer layers will envelop the inner planets, potentially engulfing Earth. Even if Earth survives this phase, it will be subjected to intense heat and radiation, making it uninhabitable. Long before the Sun becomes a red giant, increasing solar luminosity will affect Earth's climate and atmospheric composition. Researchers predict that in about 1 billion years, rising solar output will lead to the breakdown of carbon dioxide in the atmosphere, reducing the availability of CO2 for photosynthesis. This will cause the extinction of oxygen-producing organisms and a decline in atmospheric oxygen levels. The deoxygenation process could occur over a period of 10,000 to a few million years, ultimately leading to a loss of breathable atmosphere and the extinction of most life forms. This gradual process highlights the inevitability of Earth's transformation into an inhospitable environment. Humanity has a significant amount of time to develop technologies and strategies for survival beyond Earth. Potential solutions include space colonization, terraforming other planets, or building self-sustaining habitats in space. These solutions require advancements in technology, resources, and international cooperation. Exploring and developing the necessary infrastructure for off-Earth living will be essential for ensuring the long-term survival of human civilization. The potential end-of-life scenarios on Earth offer valuable lessons for humanity. They underscore the importance of environmental stewardship, scientific research, and technological innovation in preparing for and mitigating existential threats. Understanding these scenarios helps us appreciate the complexity and fragility of our planet's systems and emphasizes the need for proactive measures to ensure our survival. One of the key lessons is the need for environmental stewardship. The prospect of deoxygenation and other catastrophic events highlights the importance of maintaining the balance of Earth's ecosystems. Human activities, such as deforestation, pollution, and climate change, are already disrupting natural processes and contributing to environmental degradation. Protecting and restoring natural habitats, including forests, wetlands, and marine ecosystems, can enhance biodiversity and support the resilience of the biosphere. Promoting sustainable development practices that balance economic growth with environmental conservation can help ensure the long-term health of our planet. Advances in scientific research and technology are vital for understanding and addressing existential threats. Continued investment in space exploration, climate science, and environmental monitoring can provide the knowledge and tools needed to mitigate potential disasters. Supporting programs that monitor and track near-Earth objects, NEOs, can help identify potential asteroid threats and develop strategies for deflection. Investing in climate research can improve our understanding of climate change and its impacts, enabling more effective mitigation and adaptation strategies. In addition to these measures, humanity must consider the long-term implications of our actions and the need for preparedness. Exploring and developing space-based solutions for survival beyond Earth, such colonizing other planets or building self-sustaining habitats, will be essential for ensuring the continued existence of human civilization in the face of cosmic and environmental threats. Asteroid impacts, gamma-ray bursts, deoxygenation, and the aging of the Sun all present potential doomsday scenarios that could end life on our planet. Understanding these threats, their mechanisms, and their historical contexts is crucial for preparing for and mitigating their impacts. The lessons we can draw from these scenarios emphasize the importance of environmental stewardship, scientific research, and technological innovation in ensuring the survival of life on Earth and the continued existence of human civilization. By taking proactive measures to protect our planet and explore opportunities for survival beyond Earth, humanity can navigate these challenges and secure a future for generations to come. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.